All right, welcome back to Dynamics. Today we're going to be getting into a method where we're combining now the two worlds of uh, the linear and the angular, right? We've learned how to come up with SV and A, linear position, velocity, acceleration, and we did the same with theta, omega, and alpha. And now we need to combine them for when we have both going on, translation and rotation. There's multiple ways to do it, and the first way we'll try today is called absolute motion analysis, where we're essentially relating the linear motion to an angular motion using geometry. So something like this dumpster, right, that's both lifting as this hydraulic cylinder pushes on it and rotating as it does that. And if we could come up with a relationship using just geometry, right? Like the fact that this is a triangle. Maybe we use a law of sines or a law of cosines or sines and cosines or tangents or something else geometrical to relate the change in length s, so that would just be a side of the triangle s, related to the angle theta. If we can come up with that relationship, then we have something that we can take a time derivative of. And the time derivative gives us v in terms of now omega. Take a time derivative again, we've now got a in terms of alpha. And it's not just going to be r times theta equals s anymore, unless it's something really simple. And we'll see that today. But usually it's going to be some other relationship that is more interesting because of the more complex geometry and movement. That's not just a fixed axis rotation like we did last time. So it could be something like this, right? We've got a fixed axis that's rotating, but the center of gravity is also translating. Excuse me. So if we wanted to come up with the motion s in terms of theta, then we could say, oh, look, there's a triangle there. S could be related to theta using maybe the law of cosines, for example. And if we could get that s in terms of theta, that's what we're gunning for. That's what we're aiming to get so that we can do a time derivative twice and get the velocity and accelerations. Here's another example that we'll actually look at today. This would be pretty typical, right? You've got some RPMs desired here, and then this is going in and out at some rate here. What's the relationship between those? Well, maybe you could bust this into two triangles and you could have the left side that's a right triangle and the right side that's another right triangle. And their bottoms would equal this length, and we could somehow come up with that length x in terms of theta. And then that would tell us, well, if we're going to certain RPMs, this will go in and out at a certain rate, right? Or the other way around, right? So that could be really useful. So the absolute motion analysis, the way we're going to do this is essentially, like I was saying, come up with some geometric relationship somehow between s and theta, the linear and the angular. And once we get that relationship, and really that's the hard part, is make a geometric relationship that relates some length s or x or whatever you want to call it in your picture, and that relates it to the angle theta. Then we're just doing first and second time derivatives, right? We do have to be a little bit careful that if we have functions of, say, theta or omega inside of another function, like a tangent or a cosine or something like that, or maybe an exponent, right? Now we've got chain rules that we have to be careful with. But in essence, that's all we're doing, right? Establish what our s is. What's that length that's changing? Then establish what our theta is. Pick some axis that is rotating about and say, okay, there's our theta. And then come up with a geometric relationship between the two, right? Use trig, use basic geometry, you get a little creative, you come up with that relationship. And really, that's what we need, right? S equals blah, 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 theta, right? We need it to relate those two variables. Then the rest is all just calculus. So then, yeah, like I said, take the first time derivative, you get v in terms of omega now, do it one more time and you get a in terms of alpha. So it's a beautiful thing. We'll wrap up this video with a quick example then. So this is a really simple one, but if we wanted to say how far does it move linearly, so this distance sg, when it rolls a certain amount theta, right? When it goes a certain number of radians, how far does that go forward? Well, that'll be some relationship of its circumference, right? As it rolls forward some angle theta, it moves r times theta arc length, right? And that was a relationship we talked about last time. So really, that's all it is for this one. How do we relate s to theta? Well, it's just s equals r times theta. So this one really was that simple. But if we could get that, what's v? Well, time derivative of ds dt would just give us v on the left side. D r theta dt would be the right side. And we'd end up with r times the d theta dt, which is omega, right? So we'd have v equals r times omega. You could do another one for a. Another derivative, you would get a equals r times alpha. So pretty simple for that one. In the next example, we'll get a little more interesting and actually have to do a little bit more of some trig functions or something else geometrically to come up with our relationship between the linear and the angular. But then the rest of the process is just calculus.